everyone. Your presenter for this next topic is Jannie Llanera, BSCE 3A. So the previous subtopics under abstraction from precipitation was about evaporation process and evaporators. And now we're going to tackle the next subtopics, which are the empirical evaporation equations, analytical methods of evaporation estimation, and reservoir evaporation and methods for its reduction. First, we're going to discuss about empirical evaporation equations. To estimate lake evaporations, there's a large equations available using commonly available meteorological data. Most formulae are based on the Dalton type equation and can be expressed in general form. E subscript L is equals to K times the function of U times E subscript W minus E subscript A, where E subscript L is the lake evaporation in millimeter per day, E subscript W is the saturated vapor pressure at the water surface temperature in millimeter of mercury, E subscript A is the actual vapor pressure of overlying air at a specified height in millimeter of mercury, and the function of U is the wind speed correction function, and K is a coefficient. The term E subscript A is measured at the same height at which wind speed is measured. There are two commonly used empirical evaporation formulae, and those are the Mayer's formula 1915 and the Rower's formula 1931. So for Mayer's formula 1915, the equation is E subscript L is equals to K subscript M times E subscript W minus E subscript A times 1 plus U subscript 9 all over 16, where U subscript 9 is the monthly mean wind velocity in km per hour at about 9 meter above ground, and K subscript M coefficient accounting for various other factors with a value of 0.36 for large deep waters and 0.50 for small shallow waters. Next is the Rower's formula 1931. Rower's formula considers a correction for the effect of pressure in addition to the wind speed effect and is given by the equation below, where P subscript A is the mean barometric reading in millimeter of mercury, and U subscript 0 is the mean wind velocity in km per hour at ground level, which can be taken to be the velocity at 0.6 meter height above ground. Empirical formulae that are given can be at best be expected to give an approximate magnitude of the evaporation. Next, often the wind velocity data would be available at an elevation other than that needed in the particular equation. However, it is known that in the lower part of the atmosphere, up to a height of about 500 meters above the ground level, the wind velocity can be assumed to follow the 1/7 power law as U subscript H is equals to C times H raised to 1/7, where U subscript H is the wind velocity at the height H above the ground and C is a constant. So here is an example. For letter A, the problem is a reservoir with a surface area of 250 hectares had the following average values of climate parameters during a week. Water temperature is equals to 20 degrees Celsius, relative humidity is equals to 40%, wind velocity at 1.0 meter above ground surface equals to 16 km per hour. Estimate the average daily evaporation from the lake by using Mayer's formula. So the solution for problem A is a given water temperature is equals to 20 degrees Celsius. We can get that based from the table, the value for E subscript W is equals to 17.54 millimeter of mercury. Thus, for the value for E subscript E, we multiply 17.54 and the 40% given, which is the relative humidity, from which we convert to 0.4. So, 17.54 times 0.4 is equals to 7.0 millimeter of mercury. The value for U subscript 9 is U subscript 1 times 9 raised to 1/7 equals to 21.9 km per hour. We then substitute the values we got using the Mayer's formula. So to solve for the lake evaporation, E subscript L is equals to 0.36 times 17.54 minus 7.02 times 1 plus 21.9 over 16. Thus, we get 0.97 millimeter per day for the lake evaporation. For letter B example, an ISI standard evaporation pan at the site indicated a pan coefficient of 0.80 on the basis of calibration against controlled water budgeting method. If this pan indicated an evaporation of 72 mm in the week under question, first, estimate the accuracy of Mayer's method relative to the pan evaporation measurements, and second, also estimate the volume of water evaporated from the lake in that. For the solution, daily evaporation as per pan evaporimeter is equals to 72 divided by 7 times 0.8 is equals to 8.23 millimeter. Error by Mayer's formula is equals to 8.23 minus 8.97 is equals to negative 0.74 millimeter. Hence, Mayer's method overestimates the evaporation relative to the percentage overestimation by Mayer's formula is equals to 0.74 over 8.23 times 100 is equals to 9%. Next, considering the pan measurements as the basis, volume of water evaporated from the lake in 7 days is equals to 7 times 8.23 divided by 1000 times 250 times 10 raised to 4 is equals to 144,025 cubic meter. For the next subtopic, Analytical Methods of Evaporation Estimation. For the determination of lake evaporation can be broadly classified into 3 categories as water budget method, energy balance method, and mass transfer method. Water budget method. It involves writing the hydrological continuity equation for the lake and determining the evaporation from a knowledge or estimation of other variables, thus considering the daily average values for a lake. The continuity equation is written as P plus V subscript IS plus V subscript IG is equals to V subscript OS plus V subscript OG plus E subscript L plus delta S plus T subscript L, where P is the daily precipitation, V subscript IS is the daily surface inflow into the lake, V subscript IG is equals to daily groundwater inflow, V subscript OS is the daily surface outflow from the lake, V subscript OG is the daily seepage outflow, E subscript L is the daily lake evaporation, delta S is equals to the increase in lake storage in a day, and T subscript L is the daily transpiration loss. All quantities are in units of volume, cubic meter, or depth, millimeter over a reference area. The continuity equation can be written as the equation below. In this, the terms P, V, IS, VOS, and delta S can be measured. However, it is not possible to measure VIG, VOG, and VL, and therefore these quantities can only be estimated. Energy budget method. It is an application of the law of conservation of energy. The energy available for evaporation is determined by considering the incoming energy, outgoing energy, and energy stored in the water body over a known time interval. Considering the water body given in the figure, the energy balance to the evaporating surface in a period of 1 day is given by Hn equals to Ha plus He plus Hg plus Hs plus Hi, where Hn is the net heat energy received by the water surface, which is equivalent to Hc plus opening parenthesis 1 minus R closing parenthesis minus Hb. Hc close in parenthesis 1 minus R closing parenthesis is the incoming solar radiation into a surface of reflection coefficient albedo R. Hp, back radiation long wave from water body. He, the sensible heat transfer from water surface to air. He is heat energy used up in evaporation, equivalent to density times Le subscript L, and Hg, heat flux into the ground, Hs heat stored in water body, Hi net heat conducted out of the system by water flow or the advected energy, and all the energy terms are in calories per square millimeter per day. All the terms except Ha can either be measured or evaluated indirectly. The sensible heat term Ha, which cannot be readily measured, is estimated using Bowen's ratio, beta, given by the expression beta is equals to Ha over density times Le subscript L equals to 6.1 times 10 raised to negative 4 times P subscript A and multiplied to T subscript W minus T subscript A all over E subscript W minus E subscript A, where P subscript A is the atmospheric pressure in millimeter of mercury, E subscript W is saturated vapor pressure in millimeter of mercury, E subscript A is the actual vapor pressure of air in millimeter of mercury, T subscript W is the temperature of water surface in degrees Celsius, and T subscript A is the temperature of air in degrees Celsius. With the two given equations, Hn equals to Ha plus He plus Hg plus Hs plus Hi, and the beta equals to Ha all over density Le subscript L, we can evaluate E subscript L into Hn minus Hg minus Hs minus Hi all over density L times 1 plus beta. Is the process on how the estimation of evaporation is derived. Mass transfer method. It is based on the theories of turbulent mass transfer in boundary layer to calculate the mass water vapor transfer from the surface to the surrounding atmosphere. So the next subtopic is about the reservoir evaporation and methods for its reduction. For the water volume lost due to evaporation from a reservoir in a month is calculated as VE equals to AE subscript PM times C subscript P, where V subscript E is the volume of water lost in evaporation in a month, cubic meter. A is the average reservoir area during the month, square meter. E subscript PM, pan evaporation loss in meters in a month, meter. Or E subscript L in millimeter per day times the number of days in the month times 10 raised to negative 3, and C subscript P is relevant pan coefficient. Evaporation from a water surface is a continuous process. Typically under Indian conditions, evaporation loss from a water body is about 160 cm in a year with enhanced values in arid regions. The quantity of stored water lost by evaporation in a year is indeed considerable, as the surface area of many natural and man-made lakes in the country are very large. While a small-sized tank or lake may have a surface area of about 20 ha, large reservoirs such as Narmada Sagar have surface area of about 19,000. For the next slide, there is a given table. It is the surface areas and capacities of some Indian reservoirs. It is the table about water loss due to evaporation, volume in cubic kilometer. Reduce evaporation losses. 1. Reduction of surface area. Volume of water lost by evaporation is directly proportional to the surface area of the water body. Thus, the reduction of surface area wherever feasible reduces evaporation losses. Measures like having deep reservoirs in place of wider ones and elimination of shallow areas can be considered under this category. Second, mechanical covers. Permanent roofs over the reservoir, temporary Roofs and floating roofs such as rafts and lightweight floating particles can be adopted wherever feasible. Obviously, these measures are limited to very small water bodies such as ponds, etc. Third is the chemical films. This method applying a thin chemical film on the water surface to reduce evaporation. Currently, this is the only feasible method available for reduction of evaporation of reservoirs up to moderate size. Monomolecular layers on a water surface. These layers act as evaporation inhibitors by preventing the water molecules to escape past them. The thin film formed has the following desirable features. Number 1, the film is strong and flexible and does not break easily due to wave action. Number 2, if punctured due to the impact of raindrops or by birds, insects, the film closes back soon after. Number 3, it is pervious to oxygen and carbon dioxide. The water quality is therefore not affected by its presence. Number 4, it is colorless, odorless, and non-toxic. Certain chemicals, such as cetyl alcohol and stearyl alcohol, form monomolecular layers on a water surface. Cetyl alcohol is found to be the most suitable chemical for use as an evaporation inhibitor. It is a white, waxy crystalline solid and is available as lumps, flakes, or powder. It can be applied to the water surface in the form of powder, emulsion, or solution in mineral turpentine. Evaporation reduction can be achieved to a maximum if a film pressure of 4 times 10 raised to negative 2 Newton per meter is maintained. The major impediment affecting the efficiency of these chemical films is the adverse effect of heavy wind. To sum up the idea, we use empirical equations because the amount of using sophisticated instruments are very expensive. Thus, it is more easy to use estimation process in determining the needed essential computations, but the results are not accurate. And as for the reservoirs, they are the biggest man-made source of water, but large amount of water are being wasted because of evaporation. Evaporation is faster in reservoirs compared to other water resources. That's why proper methods are used to reduce evaporation loss. And that's all. Thank you.